Basics of blast wave theory. Week 4. Shock waves, revision. Hydrodynamic theory of shock waves.
Okay, regarding shock waves, what are shock waves and how they are produced? Now, just to clarify the concept, there are many examples which are given what basically shock is. Now, this runner, I like this, just a matter of taste. We think of some people standing equidistance, not too close, not too far. Many people, and then we ask one person to run by those people and touch the person. Now, the instruction given to these people standing is that as soon as you feel a touch, start running. So, just try to imagine what would happen after some time. After some time, the distance between these running people would be less, and those who had not been touched yet would be again at the same distance. Now, if I define density, number of people over a certain length, then you might see here there was one density undisturbed, but here this is density profile. There is some area where almost no person, and those persons have accumulated in here. Now, this is what happens when we deposit energy into some medium rapidly. Very quickly we deposit energy. Now, that energy had to transfer to this surrounding. Now, the rate at which the energy is dispersed in the surrounding may be less than the injection time. If the injection rate is very high and dissipation rate is low, then there would be accumulation of energy. Like in this example, if we try to plot the density, so the density would look like this one. So, we get accumulation of energy, of density or of material, so to say. Now, we can call this as a shock front. This can be considered as a shock front. The second example, that of traffic, that is reversed to this one. Now, imagine these are vehicles almost equidistant traveling in this direction, and then the first driver sees some obstruction in front. So, what would happen? That person would pull a brake, and the rear driver see with a little bit lag and then pull the brake. So, what would happen? Same kind of car density distribution would appear, but you see the stopping signal is originating from the rear of the vehicle, and in that case the wave would be moving in the backward direction. In the first example, wave head was that person who was touching to signal the runner that you start running, correct? So, now here this wave motion is in the reverse direction, and instead of acceleration there is a deceleration. So this is very famous problem, many mathematicians have done it, and this is being used in traffic jams, and there is a shock which moves backward against the flow of the traffic when you get a jam or congestion. So these are just conceptual ideas. Next we see when we burn coal in air, so this is the amount of energy released per gram, 32.5 kilojoule, but it takes quite some time, around 2 minutes, to release that energy. As compared to TNT, if we detonate 1 gram, it releases only 2.175 kilojoule. But the energy release here is in 1 microsecond. So if you compare the energy, about 16 times more energy had been released. And there is no bang, we don't listen any bang, no explosion. But 1 gram of TNT, there can be a very loud explosion. Loud explosion means a high strength shock wave reaching us, converting into sound. And if we are very close to this one, it can damage us. But usually we are far away, that's why we hear a bang. Now what is causing a bang or what is generating a shock wave is this power. You see, in case of TNT, same 1 gram, the power is about 2.175 megawatt. Simply, we divide energy by time, so we get this much megawatt. There we divide this energy with time and we get only 0.271 kilowatt. Correct? Now, you can safely say if the power injection is high, then there would be a generation of shock wave. When the power injection is low, there won't be any shock wave generated. Now, this is just the conceptual. I have written in here rapid transport of energy. So this shock is a mode of energy transport also. But this is very efficient energy transport, very quickly. Next comes mathematically, what is a shock wave? So we can say it is a jump discontinuity. And how it arises, in a moment we see it. We go to look into hydrodynamic theory of shock waves. Now, we need to quantify things, because when you want to predict something or if you want to calculate something, you need to know some kind of a law, some kind of an equation, differential or algebraic, doesn't matter. Now, let us try to transform these vague concepts into something concrete in the form of relations. Now, this is our common observation that rate of change of pressure with respect to density, or in other words, partial P by partial rho, when we keep entropy constant. This is some positive quantity, remains always positive, and we can call it velocity of sound, square of velocity of sound. Now, velocity of sound increases with increase in density. This might be known to many of you that velocity of sound is larger in water compared to air, because in water we use sonars to detect objects, but we cannot use sound wave to detect aeroplanes in atmosphere, because sound is too slow compared to the objects moving in which we are interested, especially the supersonic aeroplanes. So we use radar waves to detect them. But the same sound wave can be used to detect moving objects inside the water. We call them sonars. So velocity of sound is larger in water compared to air. Agreed? Okay. Now, why it is larger? Because nature had created things upon reasons. There must be certain reasons. So we look at the characteristic. Higher density is one of them. Correct? So when the density of the material increases, the velocity of sound increases in that. Correct? Okay. Now let me come back to air. Now, sound wave, we know it is a disturbance. Like in water, when we throw a pebble, we see some movement. So there is not a very big amplitude, a small amplitude which is moving. Now same is with the sound wave. Now in sound wave, we have something like this. This is our disturbance. This is our sound wave. Now, the density variation or the pressure variation with respect to density we can ignore for sound waves. Of course, there is a pressure change, otherwise we cannot listen to anything. There is a pressure change, but it is not very significant. So what happens if this is disturbance, weak shock wave or sound wave, and it is traveling in this direction, say, after some time the shape would be same. If this is sine wave, it would remain sine wave, no change at all. But let me call this weak shock wave. Why we call it weak shock wave? Because the amplitude is very low, the strength is low. Now, by the way, when I say strength of shock wave, now what basically shock wave is? In material there is some pressure, let me call it shock pressure. The density change is there, let me call it rho s. And then material is flowing behind the shock wave, let me call that material velocity, and there would be some internal energy, of course, of the material which is following the shock wave, so we call it epsilon s. Now, all these things are high. Of course, there would be some shock velocity also. Now, all these quantities we can call, they represent shock strength. When the shock is strong, it means the shock velocity would be quite high, the shock pressure would be quite high, density, similarly the material velocity or particle velocity, which I call internal energy, everything would be high. Now, this is called shock strength. In sound wave, we say Ps is not very high compared to P naught. Say this is P naught in this rounding. Rho naught is the density in this rounding. So, this pressure in case of sound wave is not very high compared to P naught. Correct? Similarly, the density variation is not very high. So, looking at the same formula, we can say safely, of course, there is a density difference between peak and the front. There is a density difference, but this variation is not very high, doesn't contribute too much to the velocity change. Now, let us consider shock wave. Now, shock wave strength is high, means, let me draw a high amplitude, something like this. Now, when it moves, it obeys the same formula also. The velocity, c is what? Wave velocity. Now, the velocity changes with respect to the density change. Now, here density is much higher compared to this section, for example. Here the density is many-fold higher compared to this section. So, this section would be moving with higher velocity compared to this section. So, after some time, when the velocity of this part is larger than this part, now the profile would look like something like this. It would be steepening towards the front, in which the front is moving. Okay. Let